Compounds are represented with chemical formulas. Compounds also have names, and we're going to learn a lot about those in this chapter. So a chemical formula is like a shorthand that's telling us what's in the compound. So it's going to indicate which elements are in the compound and the relative numbers of those atoms or ions. So we use subscripts following the element symbol to indicate how many of that atom are in the compound. So water is represented as H2O. H2 means that there's 2 hydrogen atoms, and the O, without any number after it, the number would be a 1, and we don't write 1s unless we absolutely have to. So this means that there's 2 hydrogens for every 1 oxygen. Another compound, carbon tetrachloride, is represented as CCl4. So this C is carbon, Cl is chlorine. So there's 1 carbon and 4 chlorines in this compound. Any questions? The capitalization of the first letter is very, very important. There's 2 capital C's here. That tells me that there's 2 elements in this compound. One is carbon, and the other, I see this capital letter, and then that's a lowercase l. We have to be careful with those because L's and 1's and capital I's can look very much alike. And so I specifically chose this font in my PowerPoint slides so that they do look a little bit different. There are different types of chemical formulas. They give different amounts of information, and they're useful in different situations. A little bit like there are different ways that you can identify an individual, right? You have your full given name, you have a nickname or your first name or whatever your friends call you, you have a social security number, you have a student ID number, all these different ways of identifying who you are. And those things are useful in different situations. So we have empirical, molecular, and structural formulas. Empirical is a word that means from experiment. Empirical formulas are derived from experimental data. They give the relative numbers of atoms of each element in a compound. They don't necessarily tell us how many atoms are in a molecule, but they just give us relative numbers. So the example here is hydrogen peroxide. So hydrogen peroxide molecules, I'll draw one of those. So here's a hydrogen peroxide molecule. And I'll use gray to represent the hydrogen. So the molecule has 2 oxygens represented by the red circles and 2 hydrogens represented by the gray, trying to be white circles. So the chemical formula that we normally use is H2O2. That's the molecular formula that we'll talk about in a minute. Tells us exactly what's in the molecules. The empirical formula gives us the simplest ratio. So 2 hydrogens to 2 oxygens, the empirical formula for this is HO. That is the simplest ratio. So you can think of it as a little bit like reducing fractions. If you had a fraction 2 over 2, that is equivalent to 1 over 1. Any questions? So the molecular formula gives us the actual number of atoms. And here are a couple of examples. C4H8. That tells us that in a molecule of that compound, there's 4 carbons and 8 hydrogens. The empirical formula for that, we would simplify that ratio of 4 to 8, and the empirical formula would be CH2. There are many, many compounds with the same empirical formula of CH2. For the compound B2H6, that's a molecular formula. If we reduce that ratio of 2 to 6, we get 1 to 3, and that's the empirical formula for that compound. We talked about this one already, CCl4. That's 1 to 4 carbons to chlorines that cannot be reduced anymore. That is already the simplest ratio. So for CCl4, the empirical formula and the molecular formula happen to be the same thing. So you should be able to identify something that is an empirical formula. An empirical formula always has the lowest ratio. 1 to 2 cannot be reduced. So these are definitely empirical formulas. If you see one that is not in the lowest ratio, then that's going to be a molecular formula. When you see these like this, these guys over here, we can say definitely those are empirical formulas. We can't say for sure without more information whether that's the molecular formula or not, because sometimes they're the same. We can also draw structural formulas. This gives more information. Here we're showing how those atoms are connected to each other. So it shows the structure of the compound. And in these structural formulas, we use a single line to represent a single bond, a double line for a double bond, and a triple line for a triple bond. So a lot of this terminology can be confusing. We are not trying to be confusing, right? Single line, single bond, right? Just kind of makes sense. Which formula we use depends on the situation, how much information we have, how much information we want to communicate. Some are easier to use than others. There's a reason that you don't always write your entire full name, first, middle, and last, right? If you're writing a note to a friend, you probably just sign your first name because the rest of it isn't needed. So a structural formula will give us the most information. An empirical formula gives us the least information. So here's a question. Write the empirical formula for the compounds represented by the molecular formulas. This is the sort of question that could show up on an exam. So for C5H12, that's the molecular formula. What's the empirical formula? It's the same. It cannot be simplified, right? A ratio of 5 to 12 is as low as you can go. So there they are the same. How about this one, Hg2Cl2? HgCl. A ratio of 2 to 2 can be simplified to a ratio of 1 to 1. I'm taking the subscripts and dividing them by the same number. The third one, C2H4O2. CH2O. I divide all those subscripts by 2. I don't write the 1 here, but it's understood. So I've got one carbon to 2 hydrogens to 1 oxygen. That's the empirical formula. Any questions? We also use molecular models. We've already seen pictures in the slides where water is represented as a red ball with 2 little white balls stuck onto it. Molecular models are more accurate and complete than structural formulas because they give us a sense of how it would look in 3 dimensions. So a ball and stick molecular model is very popular. We represent the atoms as balls and the bonds as sticks that are connecting them together. These colors here are somewhat standard, and these are the ones that your textbook uses. So the colors just make things a little easier because you don't have to specify all the time what the different atoms are. So typically we use black for carbon, blue for nitrogen, etc. You do not need to memorize these colors, okay? Don't worry about that one. We can also make a space-filling molecular model, and this gives the most accurate representation of what the molecule would actually look like. So here we have 4 different ways to represent methane. CH4 is the molecular formula. It's also the empirical formula. The structural formula shows us that all 4 of the hydrogens are connected to the carbon. If you don't know about the characteristics of hydrogen and carbon atoms, you could combine those on paper in lots of different ways. You could have them holding hands in a circle or all straight in a line, right? But this shows us how they're actually connected. The ball and stick model shows us that this is a 3-dimensional shape. It's not flat like it looks here on the paper. The space-filling model is what we would most likely see if we were able to zoom in and look at the molecule. There is not a big space between the carbon and the hydrogen atom with a stick here. That's not how the molecule actually looks. It's going to look more like this. The reason we don't use these types of models as much, especially when we're just drawing them, is one, they're harder to draw, and they're harder to see. Because these tend to obscure anything that's on the back side of the molecule, whereas the ball and stick is more open and you can kind of see through it. So here's a table from your textbook showing 4 different compounds and the various ways they can be represented. Glucose is blood sugar. Here's its empirical formula, the molecular formula, the structural formula, ball and stick model, and space-filling model. Now, on the space-filling model, you can't see all of the atoms, right? It's three-dimensional, and some of them are on the back. So this is useful in some situations and not in others. Any questions?